Hello, my name is David Lee Summers, and this is a presentation called To See New Earths. And we'll explain a little bit about why that's in quotation marks as we go along. But basically, it's a presentation about Kitt's new NEID spectrograph and how that relates to NASA's TESS mission. TESS, of course, is the Transiting Exoplanet Survey Satellite, which is looking for Earth-like planets near the sun. As I say, I'm David Lee Summers. I'm an author and an editor, and here's a sampling of some of my books, which I'm sure are available online with the dealers here at MileHiCon this weekend. And I bring these up because, of course, it's my writing that brings me to MileHiCon, and that's the reason I'm here. I'm not actually paid by the observatory I work for to do these presentations, but I am also an astronomer. And here you see me with Ethan Peck, who plays Spock in Star Trek Discovery and Will in Star Trek Strange New Worlds. We're actually standing in the entryway of the WIYN Telescope where the NEID spectrometer is being installed. And of course, you know, this is an important science project if Mr. Spock comes to check you out. So what is this NEID spectrograph and Kitt and all of this? So for those of you who might not be familiar with it, Kitt National Observatory is located southwest of Tucson, Arizona. It is on the land of the Tohono O'odham people. We are actually out on the reservation, and the federal government leases the observatory mountaintop from the tribe. And we're probably most famous as the largest collection of astronomical telescopes on a single mountaintop. And just to kind of give you some perspective of the telescope I'm going to be talking about, if in the picture here, if you can see my mouse, basically the telescope over here on the far left side that's got kind of an octagonal silver structure is the second largest telescope on the mountain, one of the newer ones. That's called the WIYN Telescope. WIYN is W-I-Y-N. It stands for Wisconsin, Indiana, Yale, and NOAO, which were the original partners who built the telescope. As I say, it's the second largest telescope on the mountain. The largest and probably most famous is about a mile away, and you can see it in about the center of the image here. It's the one that basically has a, that's the one that's a very tower-looking one on the mountain, kind of in the background, and that's our 4-meter or 158-inch telescope. And that's probably the most famous, longest-serving telescope on the mountain. It is the telescope that is famous because it's where Vera Rubin worked and discovered the evidence for dark matter. So, but we're mostly going to be focused on the WIYN telescope, and here it is. This is what it looks like inside the dome. This telescope was opened in 1995, and I was actually one of the first 4 operators on the telescope. And when we talk about how big a telescope is, when we say it's 3.5 meters, what are we talking about? We're actually talking about the size of this big mirror here that you see underneath these sort of rectangular square mirror covers that are folded up to the side. And that's the primary optic of the telescope. In old-fashioned refracting telescopes, that primary optic would be a lens up at the front top end of the telescope. Nowadays, we mostly make all telescopes as reflectors because you can fold the light and you can make much bigger optics. So light comes in, comes down, hits the primary mirror down here at the bottom, goes up to a secondary mirror in the sort of black can up at the top end of the telescope, and comes down to a third tertiary mirror in the center. And that mirror can rotate, and we can actually mount up to 4 instruments at a time. One instrument is over on the left-hand side, one's over on the right-hand side, and NEID, the one that we're going to be talking about mostly, is playing peekaboo on the back. And some of what makes this telescope very unique as a telescope is it is a much newer design telescope than many of the other ones on Kitt Peak. One of the things it incorporates is an active optics design. What that means is that there are a number of motors on the back of the primary mirror that actually push and pull it throughout the course of the night, actually make it deform it so it gets the very best possible shape for where it's pointing in the sky. Another thing that makes this unique is that in NEID and some of the other instruments, we actually have what we call a tip-tilt adaptive optics system, which tries to help take out some of the atmospheric effects of looking at the sky. So any little distortions, any heat waves, any motion that comes from wind or clouds, we try to take that out by getting the maximum amount of energy onto, light energy onto the detector. And another thing that's worth pointing out while we're looking at this picture is when you actually stand at the WIYN telescope, it's not a very large telescope, as you might be able to tell from the picture of the ladder there in the background. I actually stand, when I'm standing on the floor, I look right into the primary mirror. I'm about 6 feet tall, so that might give you an idea. This is actually physically a very small telescope for how big its mirror is. And part of that is done because of this being a telescope built in the 90s. It's an altitude azimuth telescope. That means one drive is mounted on the floor and basically rotates parallel to the floor. And then the other is an elevation axis, kind of like an old-fashioned radar mount. And these kinds of, what makes this really nice is that you can build telescopes cheaply when you do this. What makes them tricky is that you have to control all of the axes by computer. So this is something that pretty much a telescope design that really couldn't get going until we got into the 90s. So what we're going to be talking about a lot in terms of NEID is spectroscopy. And I suspect several of you know what this is, but just to give you a little background, spectroscopy is a technique that astronomers have been employing for a little over about 150 years. The technique was discovered by an optician and a physicist named Joseph von Fraunhofer back in the early 19th century. And what he discovered, of course, for, as opticians knew for a long time, you could take light and put it through a prism and you basically get a rainbow out of it. But von Fraunhofer's big discovery was finding out that if you looked at chemicals, at gases, clouds of gas, and if you put a bright source of light on the other side of that cloud of gas, you would get a characteristic fingerprint of, you would get this characteristic fingerprint of dark lines in certain parts of the spectrum, in certain parts of this rainbow spectrum. And what this fingerprint tells you is it's actually directly tied to what chemical elements are in that gas. The same thing basically happens if you're not looking directly at the light, if you're just looking at the illuminated cloud of gas. But instead of seeing dark lines in a bright spectrum, you'll actually see what we call emission lines or bright lines against a dark background. But the lines are in exactly the same place, whether you're looking at an emission line spectrum or an absorption line spectrum. Now, for an instrument like NEID, we of course are interested in things like what the stars, planets might orbit or made of, but we're actually going to use these lines for a slightly different purpose than getting to the chemical composition of the stars. We're going to use them to look for the motion of planets around those stars. So again, something that probably many of you are familiar with is the Doppler effect. And a lot of us, I live near the train tracks in Las Cruces, New Mexico, and I hear the trains go through at least once a day. And I'm used to the Doppler effect as the trains blow the whistle. As it comes closer, the frequency gets longer and longer, lower and lower frequency until it passes by me. And again, the same thing actually happens in light. And you've probably heard of red-shifted and blue-shifted light. So basically, as an object moves towards you, the light moves towards the blue end. Now, how you can actually measure this is if you have a star, a planet going around a star, or if you have let's just say a little simpler, a star moving toward you, those spectral lines that we talked about are going to be, they're going to be in the same place relative to each other, but what's going to happen is they're going to move towards the blue end of the spectrum. That's what we mean by blue shift. If the star is moving away from you, they're going to move towards the red end of the spectrum. You're going to get a red shift. And so here in this GIF, we basically get what this looks like when you're looking at it with planets. Is in this case, the cartoon is showing us not a planet going around a star, but actually a star moving around a solar system center of mass as moved by a planet. And you can see that as the planet pulls it towards us, the light moves towards the blue. As the lines move towards the blue, as the planet moves the star away from us, those lines move toward the red. Now, as you can imagine, planets moving stars, this is a pretty small motion. It's also, but there is an interesting effect, is depending on the size of the planet, the lines, how far they move towards the red or the blue, is a measure of the velocity that the star is moving. So a bigger planet, a more massive planet, moves the star faster than a smaller planet. So in our solar system, Jupiter moves the sun much faster than the Earth. And we'll kind of see that illustrated in this slide. And this was basically an infographic that came out when NEID was first being proposed, and NASA was looking for people to actually build the instrument. And the specifications are that we really want to be able to find Earth-like planets around sun-like stars. And a lot of the planets we have found around other stars so far are fairly big planets around fairly small, dim stars. And so just to give you an idea of what the difference between different kinds of planets affecting the sun are, our own suns wobble when moved by Jupiter. The sun gets moved about 29 miles per hour based on contributions from Jupiter. The Earth only moves it about 0.23 miles per hour, or almost 100 times less than Jupiter. And they kind of have a fun comparison here down below to say that a rabbit is about the speed of the sun's wobble due to Jupiter, whereas the sun's wobble due to Earth is more like the speed of a desert tortoise. So we really have to have really high resolution to be able to see Earth-sized planets moving sun-like stars. So NEID is what we call an extreme precision Doppler spectrometer. The name, this acronym, is actually this very heavily nested acronym. It stands for NN Explorer, which is a program run by NASA and the NSF. NN Explorer, Exoplanet Investigations with Doppler Spectrometry. So where did that come from? Well, part of the reason that acronym was chosen was that NEID is actually the Tohono O'odham word meaning to see. So hence the title of the talk. We're using this spectrograph to see new Earths. And again, its goal is to detect Earth-sized planets around sun-sized stars. So the WIYN Telescope has had a history of supporting other space missions. It supported the Kepler mission, which is, people are probably familiar with as a telescope that was finding all kinds of stars, literally thousands of stars around other, or thousands of planets rather, around other stars. And the way Kepler worked was Kepler was designed to look at one part of the sky, which is shown in the image here in the lower right, where basically you have just this one narrow spot in the sky and just literally counting how many planets there were in that. Now, we have instruments on the WIYN telescope without NEID, some older spectrographs that we were able to use to confirm the existence of some of those planets. But one of the really notable discoveries was with an instrument called the speckle interferometer, where what they did was they basically followed up all of the Kepler observations looking at stars with planets around them. And what speckle is it's a way of imaging stars very quickly. Normally, when we take a picture of the sky through a telescope, we open the shutter of the camera and let it sit there for minutes, if not hours, and collect as many photons, as much light as we possibly can, then close the shutter. The great part about that is you can get really detailed, deep images of things. The problem is the atmosphere has been moving all through that, and it smears a lot of detail out. Speckle is a way of imaging the sky that doesn't smear so much detail out, although it makes kind of these kind of speckly looking images, which is where the name kind of comes from. But what it determined was that about half the exoplanets discovered by Kepler are actually orbiting binary stars. And that was something that Kepler could not determine alone. So we're talking about getting extreme precision, finding these sort of tortoise speed planets, tortoise speed motions of stars around caused by Earth-like planets. How do we get that? Well, one of the first things we need to do is we need to build our spectrograph very, very carefully. So we actually build a spectrograph that's thermally controlled. You want to very carefully control the temperature so that nothing is making parts of the spectrograph move with respect to each other. You want to shock control the thing. You don't want people walking around near the spectrograph, bumping into it, doing anything like that. You want to keep dust out of it. You really want no outside influences at all. And so the actual spectrograph is built inside this unit that I kind of think of as the sarcophagus. That's not what they actually call it. They just call it the chamber and the cryo chamber and all of that. But it really does look like this big, carefully controlled tomb with the grating. Now, we've talked about spectrum being produced by a prism. Most of the time, what we do is we actually take glass and cut careful lines in it, which also breaks apart the light like you would get through a prism. And then we have a really high precision camera in here. When people are finished working on it, this all gets sealed up, and then this whole sarcophagus in the center and right-hand images get sealed up in almost this whole tomb-like structure, and the whole thing is in a clean room downstairs. So of course, this is not on the telescope. So how do we get light from the telescope down to the sarcophagus-looking thing downstairs? Well, we do that with something we call the port adapter. And this is actually the WIYN telescope around from the other side from what we looked at it in the last picture we saw of it. And here you see the NEID port adapter sitting there right smack in the center of the telescope. It's actually labeled right here. And that's a big box. And what is in that box is basically two fibers. One of the fibers takes light from the sky and takes it down to that crypt-like spectrograph. The reason the box is so big for something that's more or less just got fibers in it is that it's also got an adaptive optics tip-tilt system in it. It has guide cameras. It has all kinds of calibration equipment, and that's where the other fiber comes in, because you want a fiber that has a known light source on it that you can also send down and compare to the light that's coming in from from space, basically. And so here we see a picture of Sarah Logston. She is the NEID instrument scientist at WIYN. And what she is holding there, and the reason she's smiling so big, is that this is actually the fiber that runs from upstairs up at the telescope down 2 stairs, down 2 floors to the actual spectrograph below. And what you see in the center is that's bright light. That's basically someone downstairs shining a flashlight down in the fiber. And that was our moment where we knew we had run the fibers and knew we had not broken anything, shipping everything out from where it was built in Pennsylvania to out to the WIYN telescope, and then actually installing it on the telescope. So, and because you are seeing a lot of light there, I use that as a great demonstration that we do have tremendous throughput through this fiber, so that we're actually getting just as much light from the telescope as we can ported down into the instrument down below. So we actually got first light on this instrument in the autumn of 2019. And the way a lot of telescope projects work is people are working at all different kinds of institutions, and they bring them into a place like Kitt Peak. And here we actually see the scientists, engineers gathered around a laptop where they had their software installed, and we're actually just sitting in kind of the informal lab where we do a lot of building things, and we're looking, gathered around nervously trying to see whether or not we actually get a first light image. And sure enough, we come in and we actually see the star, and we see the spectral lines that we hope to see. And here you see several of the members of the NEID team gathered around. So what does this actual data look like? Here's the actual first light image. This was a star called 51 Pegasi. And basically what you see is in the right-hand half of this image, this sort of rainbow looking structure here is the full spectrum of the star. And the grading we're using is what they call an Echelle grading. And what that does is, if this was one long spectrum, you would see this thing just stretched, you know, however long this is, a few inches on my screen, but multiply that by however many lines you have across the room. The idea is an Echelle spectrum basically folds it over so that you get the different parts of the spectrum in these layers. We blow that out, blow that up so that we can see better what's going on in the stuff over here on the left-hand side of the image. And in fact, you can see in the midst of the spectrum, you actually see some of these dark lines, some of these absorption lines in the middle of the spectrum. And that's exactly what we're going to be looking for. The dots up above are from that calibration fiber I told you about. And the idea is this gives us a real-time way to actually measure how much those lines are moving as we monitor the star over time. This particular star was picked because it was actually the first sun-like star where an exoplanet was found back in 1995. So where we're at in this project is, when I first proposed this talk to give to MileHiCon, I thought I would have all kinds of data and results to share with you. Where we were was we're commissioning the instrument, which means we're testing everything, making sure it all works as it should, and trying to get all of the data out of it and getting the first data. And then we hit March of 2020, and I partly also show this image to show, I think a lot of people have the image of astronomers working at the telescope being, you know, the one person sitting out on a cold platform looking through an eyepiece. In fact, at the WIYN Telescope, when NEID is running, we have a control room full of people not at all socially distanced. So we actually were in the position where in March we had to close everything down, warm up the instrument. Everyone has basically been working very hard since then to figure out how to make operations work so that we can come back and then we can come back and actually operate things safely and continue the mission. So the plan is we will actually be getting back on Sky this month, this October, and continuing with the work of this. Now, as I said, NEID is there to support the TESS mission. TESS, as I said, I believe I've already said, is the Transiting Exoplanet Survey Satellite. It was launched in April of 2018, began its science operations in July of 2018, and it has already surveyed the nearest 500,000 stars around Earth. It actually completed its primary science mission this past summer, July 2020. And it's made one complete pass of all of the parts of the sky it was going to look at. So, of course, this begs the question, how are we supporting it if it's already completed its science mission? Well, part of the answer is right here. So far, TESS has discovered 74 confirmed planets, but has over 2,200 candidate planets. Now, to be a confirmed planet, what that means is that some telescope besides TESS has observed the planet. And so one of the important telescopes devoted to doing that is WIYN, which has been closed down. So we will be in the business very busily trying to look at these planets, confirming these planets, as well as looking at additional systems as well. And the other part of this is that TESS is moving into its extended mission. Of course, NASA these days has very conservative primary mission goals to build their telescopes so that they can pretty much be absolutely sure they're going to hit the primary mission goal. So now it's moving on to its extended mission, and hopefully, like the Kepler mission, it will go many times its extended mission and get to survey these stars multiple times over and over again. And as I say, this is a successor to the Kepler Space Telescope, with the difference that it's looking mostly at stars closer to Earth than Kepler did. And the important thing to know about this, though, is that TESS actually uses a different method to find planets than NEID is, and that's important for a couple of reasons. One is it means that you have more confidence when you discover a planet. You've discovered it using two different methods, and the two different methods tell you different properties of the planet. So what the transit method is it's literally looking for changes in light of the star as the planet crosses in front of it. So the planet goes in front of the star, just a little bit of the light goes away. You pretty much, once you see that 2 or 3 regular times, you know you've probably got a planet going in front of that star. One of the things that's very neat about this method is that the amount the light drops is directly proportional to the size of the planet. You might say, well, the planets might be different distances from the star. That's true, but the thing to realize is that these planets are much, much closer to their star than they are to the Earth. So by percentage, by error measurement, they're basically, from our point of view, right on top of each other. So you kind of get an outer limit to how big these things are. But so what this tells us is if you're looking at a planet going in front of the star, you learn how big around it is. You get a physical size, a radius of the planet. With our radial velocity Doppler method, you get a weight of the planet. And what's neat about if you have mass and if you have size, if you have radius, that gives you the density. And that can tell you whether you have a rocky planet, a gas giant planet like Jupiter, or an icy planet, or even a water density planet. So I've alluded to this a little bit. I've mentioned briefly habitable zones earlier in the talk, I believe. We also call these the Goldilocks zone, which of course brings to mind, the bed is just right, the porridge is just right, the chair is just comfortable enough. And what do we actually mean when we're talking about habitable zone or Goldilocks zone? We're actually talking about those planets that are far enough from their stars that water stays liquid, but not so far away from their stars that it freezes again. So where that zone is relative to its star depends on the kind of star you're looking at. So if you're looking at like a cool star, like an M dwarf, that habitable zone is going to be in much closer than it is around a sun-like star, a G star as we call it. That's just a name of a spectral type. And it's going to be, and that's even going to be closer than it is going to be for a very hot star, like an A or an O blue giant type star. So the Goldilocks zone isn't some fixed distance. So sometimes you'll hear habitable zone planets with these very short orbital periods. Well, that's because they're around cooler stars. And it's going to take, and we're going to find those planets around the cooler stars before we find them around the hotter stars. And that's faster, and that's just because the orbits are going to be faster around these cooler stars. And so I thought I would take us on a little bit, actually I was going to talk a little bit about the job of confirming planets. First, NEID's job will be to follow up on planet candidates to confirm discoveries. Of course, we'll be getting additional information on the planets that TESS has discovered. I've already talked about that the transit method gives you a diameter, the radial velocity gives you a mass. And of course, they've only been surveying these planet systems for 2 years. That's hard to get the precise orbits. If you think about our solar system, our most habitable planet in our solar system takes a year to go around the sun. They've only been looking for 2, so that means they're only maybe have made one real detection of an Earth-sized planet around a sun-like star. So, we're there, we have this instrument permanently mounted. We'll be doing, taking data on these systems for years to come. So we can do a follow-up that's even more than TESS in space can do. So with that, I thought I would go through some of the kind of interesting planets that TESS has discovered so far. So these are ones I'm sure we will be following up on with NEID. So we have one that was discovered recently, GJ357d. This is a planet in the Goldilocks zone of an M dwarf. This is a star smaller than the sun, about 40% fainter than our sun, but it's only about 31 light years away. People who were following the Kepler mission might remember that a lot of those stars are hundreds, if not thousands of light years away. Stuff is much closer. Planet D, it's in the habitable zone. It's also about 6 times Earth's mass. So we're talking about a super Earth. So this might actually be kind of an interesting world to look at to see if it actually does have water, actually is a place where life might occur. The L98-59 system is an interesting one. So far, planet B is the smallest planet that the TESS mission has discovered. It's actually between the size of Earth and Mars. And again, this is orbiting an M dwarf, so another faint red star about 5 light years away. So again, we're kind of talking, again, these are systems that are, by our current technology, still not really reachable anytime soon, but 35 light years sure sounds a lot better than 400 or 500 light years away. TOI 700 is another M-dwarf star. Maybe, this shouldn't surprise anyone because, of course, we're going to find these planets around the dwarfs, M-dwarfs, sooner than we are around like the G stars, which are what our sun is. Again, this one's a little bit further, about 100 light years from Earth. TOI 700d is in the habitable zone, but it's only about 1.6 times the size of Earth. So this is a very Earth-sized planet. To give you an idea of how much closer, though, it is to its star, it's got 2 planets inside its orbit, B and C, and planet D has a 37-day orbit. To put that in perspective, in our solar system, Mercury, I believe it has an 88-day orbit. So this is closer to its sun than Mercury is, but because it's an M-dwarf, it's in the habitable zone. Now, Kitt 9b, this is not at all going to be a habitable planet, but it's interesting for some of the things that we've talked about earlier. And it's one of the more exotic things discovered so far by TESS. So what we're seeing here is an artist's conception of the star Kitt 9 as viewed by this gas giant planet Kitt 9b, which is about 1.6 times the size of Jupiter. It's actually in a polar orbit around the star. So this is interesting because most star systems we see, most planet systems we see, actually orbit the equators like our solar system is. But for some reason, this particular planet is in a polar orbit. We have a somewhat flattened star with a large temperature gradient. And this is also stuff you can, this information about how it's rotating and how it's inclined to us are properties you can get from taking spectra. And without getting too technical, I can tell you that some of this comes from, you can get information about this by actually looking at the width of those absorption lines that we were seeing. And you can look at it by the fact that just when the star is moving, you're going to get a little bit of red or blue shift as it's moving away from, as you're looking at parts that are rotating away and towards you. So that can give you information about the rotational property of the star. So Kitt 9 is a hot A star. So this is interesting because we're actually talking about one of those blue stars where the habitable zone would be quite far out from the system. This particular planet in this particular star is about 670 light years away, so it's quite a ways away from us. But this particular planet is in, this gas giant is in very close to this bright blue star. It has a whole 36-hour year, goes around the star every day and a half. So much closer than Mercury at 88 days. TOI 1338b is TESS's first planet discovered around a binary star. The planet is actually about the size of Saturn, so we're probably talking a gas giant kind of planet. One of the stars in this is an M-dwarf, so it's a small star, but it's an exciting system because the other is actually a G star like the sun. This planet, this Saturn-sized planet, is actually in a very Mercury-like orbit around this system, orbiting the 2 stars about every 95 days. Now, you might look at this and say, well, why do we get interested in Saturn-sized planets and Jupiter-sized planets? Well, this one, it's maybe interesting, and it's going to be interesting from its own perspective astronomically, because of course we don't find gas giants in our planet system orbiting this close to suns. And in fact, when I was in graduate school, there were all kinds of theories about why it was that you could not form gas giants this close to stars. So all of that's been turned on its head. The other thing to remember is if you find a gas giant in the habitable zone, that gas giant might have moons that are habitable. So, you know, we don't give up on those just because it's a gas giant. This one, because it's a 95-day orbit around a G star, I don't think it's going to have habitable planets, but it's still a very interesting system. And this one is one of the more bizarre things, and one of the telescopes in our organization of Noir Lab, one of the Gemini telescopes on Hawaii, was involved in observing it. This is actually a survivor planet around a white dwarf star. White dwarfs are basically what happens when a star the size of the sun reaches the end of its life. What happens is the star eventually gets to a point where it expands, the outer shell starts blowing up like a big balloon and absorbing the planets that are around it. And probably in our case, it will eventually absorb Mercury, Venus, maybe even the Earth. And then eventually the whole outer atmosphere will blow off as the inner part of the star collapses into a very tiny ball, you know, a fraction of the size of the Earth. And, you know, what happens to the outer planets? What happens to Jupiter, Saturn, even Mars, or, you know, Mars or Uranus or Neptune, you know, when this all happens? That's always been kind of a mystery, because we haven't really found that many white dwarfs with planets around them. But in this particular case, what we have found is we found a Jupiter-sized planet orbiting this itty-bitty star that's about half the radius of the Earth. And this Jupiter-sized planet's going around every 34 hours. Now, they look like they're touching. They're not touching. They're more like an Earth-Moon kind of distance. But like I say, before this star became a white dwarf, it would have been about the size of the sun. So during the course of its core collapse, it pulled this planet down in towards a close orbit. And it appears to be a planet that somehow survived its star's death. So again, just very interesting scientifically to know what happens at the end of a star's life. So with this slide, I'm going to kind of talk about very generally where we are as far as planet discoveries. When I was in, I am of an age that when I was in grad school, we had the 9 planets. And yes, I'm still a believer that Pluto is a planet. I figure it's a dwarf planet, it's still a planet. But we had the 9. But since that time, since 1995, when 51 Pegasi was first determined to have a planet around it, we have now discovered 4,284 planets around 3,185 stars. 361 confirmed and candidate planets are in habitable zones, in those Goldilocks zones. The largest number of planets we have per system that we've seen outside our solar system is 8. So we do see solar systems of the scale of planets that we have. We have discovered 871 planets with radii that are kind of close to the Earth's radius. So about, you know, within about 2 times the size of the Earth. And we have about 38 planets now with masses less than or equal to 3 Earth masses. So we're kind of talking like we have about 38 planets that are sort of in that very Earth-sized kind of range. And this next slide is a little bit of an older slide. Don't take the numbers too seriously because these are a few years old at this point. But I show it because it's interesting, because it kind of shows the types of planets we found. And I think it ended up being a little different than I think people were going to expect, in that we figured we would probably see Jupiter-sized planets easier than maybe Earth-sized planets. But as you can kind of see from this, Jupiter size and larger are actually kind of rare in terms of the number of planets. The largest number of planets we actually find are around the size of Neptune and Uranus. So most of the planets we found so far are what we call ice giants. They're actually these sort of slushy worlds out past the habitable zones that are not quite gas, not quite frozen, you know, just slushy methane kinds of stuff. But we also find a lot of super Earths and Earths. And of course, you know, looking at the numbers we had just had, these are radius, not masses, like I mentioned with only the 38, but we have like about 674. Yeah, we actually have more Earth and super Earths than we do even Neptune-sized planets. So that's very exciting because, again, you're talking planets that might be a little closer to what we see in our neighborhood. So I just want to wrap up with this particular slide. It's just a place where you can look and maybe get some more information. I'll leave this up, and maybe we can put some comments, put it down into the comments of the presentation also. But anyway, we have a link for more information about the TESS mission. Basically, it's at NASA. If you go to nasa.gov and search for TESS, T-E-S-S, you can find a lot of good detailed information about the mission, read about all of these discoveries, read the actual press releases. NASA's very good about putting movies up about all of these that explain in pretty good detail what these systems are like. If you want to learn more about NEID, again, like I say, I was hoping that by the time we came to this presentation, I'd have a lot of our own discoveries to talk about, but you can kind of review some of what I've talked about. There's a good article at the Planetary Society, planetary.org, called A Win-Win Situation, WIYN-WIN. And if you look there, you can get some really good kind of talks about the instrument, talks about the science objectives. And then you can learn more about me and about what I do and about my writing at davidleesummers.com. And finally, just to let you know that there is actually a way that you as fans, as astronomy fans, can get involved in looking for these planets. If you go to planethunters.org, they will actually train for planets within the TESS data. And lots of people have discovered, citizen scientists have discovered planets in the Kepler data set. So you can be involved and maybe be involved in finding a planet. So thank you very much for coming and listening to me at virtual MileHiCon. I really wish I got to see all your smiling faces in person.